Welcome back to Containers from a Cruising Altitude. My name is Ben Rasmussen, and in this section we are going to be talking about container runtimes. At the end of the previous section, I asked you to try to think of container runtimes you've heard of other than Docker. And in this section we are going to talk about Docker and then explore other container runtimes that you can use and contrast them a little bit with how Docker works. So, Docker is by far the most popular container runtime software. And it's kind of become synonymous with images and running containers to the point where I've heard people talk about building and running their Dockers, which is a horrible way to talk about building images and running containers. Docker is, as far as I'm aware, the only major platform to support both Linux and Windows natively. Docker runs on the Docker engine, which follows the client-server model, and this is going to set it apart from many other container runtimes. In fact, I believe it's the only container runtime, at least that I'm aware of, that runs as a client-server application. So when you start Docker, you start a server daemon in the background, and that server daemon is going to host a REST API. When you make a call from the Docker CLI or from your command line using a Docker command, that call is actually converted to a REST call that is sent to the server daemon to be processed. So if you want to create a container or build an image, manage your Docker networks, those are all going to be REST calls that are processed by the server daemon in the background. This is a little heavy as far as container runtimes go, and it presents one major problem. If the Docker daemon dies, Docker dies. So if the daemon is killed for whatever reason, you can no longer run any Docker commands because the Docker CLI, once again, is just making REST calls to that server in the back. Now, it doesn't, it's fairly robust. It doesn't sporadically die, but it is a concern that you should keep in mind. Docker, its big claim to fame, because remember, it donated its image specification and its runtime specification to the OCI, and has also open sourced a lot of its underlying container runtime. So you kind of have to think, what sets Docker apart? What's their bread and butter that they're still thriving on? And that is their enterprise support and their development tools and orchestration support. So Docker has a really awesome development tool called Docker for Desktop, and it makes it super easy to download that and then be able to, run and build containers all in one simple environment on pretty much any machine that you want to. And here's a little bit of trivia for you. If I'm running on Windows, I can use Docker for Desktop to run a Linux server or a Linux image of some kind. Take a moment to think why that might work. The answer is that Docker for Desktop is actually a hypervisor in disguise. So it's not recommended for production environments, but it makes it a very convenient tool to be able to build pretty much any application you want from any host operating system you want and not have to worry about the underlying operating system. Docker also has two types of orchestration support built in, and you can think of container orchestration as essentially how do you create and manage many containers all at once. And our next section is going to talk about container orchestration a little bit more in depth, so that definition will suffice for now. But Docker does have two types of orchestration built in, and we'll talk about both of those in the next section. And they also have excellent documentation and a very well-supported community. So again, because Docker is the most popular container software, there are going to be tons of people who are both asking the same questions that you need to ask and answering those questions. And once again, with their excellent documentation, it's very easy to kind of slide into and begin working with. So, with Docker out of the way, what are some other container runtimes? The first one I want to talk about is CoreOS's Rocket. As far as I could tell, Rocket is probably the second most popular container runtime. And in the early days, they were kind of founded on the idea of being a more secure container runtime than Docker was, because initially, Docker had to be run as root. So if a process escaped Docker, it had root access. That's no longer true. Docker no longer needs to be run as root, but CoreOS Rocket is still a perfectly fine runtime. Rocket is Linux only, and even among Linux, it doesn't have full adoption, so they do have officially built versions of Rocket for certain distributions, But there are a lot of community-managed versions of Rocket as well. So, for instance, I'm a CentOS user if I need to do anything on Linux CLIs, and I had to use a community-sourced version of Rocket. Rocket is not a full suite of tools like Docker. In fact, most container runtimes are just that, a container runtime. So Rocket only manages the container runtime in the lifecycle of the container, and if you want to be able to build an image, you must use a third-party tool. Again, we have a section on that later, but one potential tool you can use to build images for Rocket is Docker. So Rocket is OCI compatible, and the way they do their OCI compatibility is a little bit interesting, I think. So under the covers, Rocket still uses a legacy specification called ACI, which is the Application Container Image Specification, and AppC, which is the Application Container Runtime Specification. Built into their Rocket run command, they have a script called OCI to ACI, which will convert an OCI image to an ACI image, which can then be fed to the AppC runtime and run as usual in Rocket. They are working on swapping out their ACI and AppC specifications for native OCI compatibility, but they at least have the script there as a stopgap in the meantime. One thing that sets Rocket and most container runtimes apart from Docker is that they do not use a daemon. They use a fork exec model. So if I'm running Rocket as process 1000, let's say on a Linux machine, and I execute a Rocket run command, it's going to execute as a child process under me. So it might be process 1001, whose parent process is 1000. Another container runtime is Podman. We're only going to touch on Podman right now because the thing that really sets it apart from other container runtimes is its lightweight orchestration support built in. So Docker has some orchestration support built in, but Docker Swarm is their kind of enterprise container orchestrator, and Podman mimics things like Docker Swarm and Kubernetes, but in a standard container runtime environment. And that's going to make a little bit more sense in our next section when we talk about container runtimes, and we'll swing back and talk more about Podman at that time. Right now, I wanted to touch on it as just a basic container runtime that you can use that allows you to do a little bit of plug and play with some of the tools that it uses. So it supports multiple image formats, most notably the OCI, and I believe it also supports ACI, but I'm not sure of that off the top of my head. And it also supports multiple means for downloading and doing image verification. So if you want to swap out what tools it's using underneath the covers to do its downloading and image verification, or even write your own, you're able to with Podman. So we've talked a bit about virtual machines and containers in the first section. And the one big advantage that virtual machines had over containers is that they had very strong isolation, and that helped their security posture. And the reason they had strong isolation over containers is because the virtualization or the isolation is enforced at the hardware level. And so there's no real concept of a process escaping the virtual machine and starting to execute code on the host. Whereas with containers, you're sharing the operating system. And there have been instances of processes escaping their container both maliciously and non-maliciously and affecting the host and all other containers running on that host. So virtualized containers are trying to bridge that gap a little bit and get the strong isolation of virtual machines while maintaining all of the benefits of containers. So running through this table real fast here, we just talked about containers have weak isolation because they share the kernel. Virtual machines have very strong isolation because they're all running their own independent operating systems. Virtualized containers are going to have strong isolations because when you deploy a virtualized container, you're actually deploying a very small stripped down kernel alongside the container, and then the container runs on that small kernel. So it's no longer sharing the kernel of the host. Boot time wise, virtualized containers are very fast. Same with containers. Virtual machines can be a little bit slower, tens of seconds to minutes. Performance wise, containers have excellent performance, especially when compared to VMs. VMs are fine. We've been using them for decades and there hasn't been any real issues. Virtualized containers aren't as good as containers, but they are going to be faster than virtual machines. And again, this can be partly attributed to having that very stripped down kernel rather than a full operating system. And image sizes, containers we've talked about previously are very small in megabytes. Virtual machines tend to be very large. Virtualized containers get that small image size. So there's really only two notable virtualized container runtimes. The first one, and the one that I think is most interesting, is Kata. And Kata is actually very new on the scene still. In fact, when I began researching this project back in January of 2019, there was very little information on Kata containers and how they were working. But as time progressed, they've actually been very active, and there have been a lot of very interesting progressions with their product. So Kata containers is an evolution of Intel Clear containers, and it's probably better to say that they absorbed Intel's Clear containers. Intel had a virtualized container product called Clear Containers, and when Kata containers came out and had all of their open source software, Intel actually donated their Clear Containers project in hopes that the community would accept it and try to essentially run better, more secure containers. So Kata containers can support one or more containers per virtual machine it deploys. And it's going to do this by using something called the Kata agent, which is running alongside the virtual machines as a monitor and a manager. So when Kata goes to deploy a new container, the Kata agent is what's going to help decide if it needs to deploy an entirely new virtual machine or if it can share a virtual machine with other containers. The runtime is OCI compatible, and it's kind of interesting to read how they implement the OCI specification, because they use the OCI specification not only to define when and how to create a new container, but also they extend it to define when and how to create a new virtual machine. And its architecture is really well documented. You can go and find it on their GitHub project, and it's a very neat contrast with Docker. Kata containers supports multiple container runtimes, notably runc, which is what Docker is using under the covers, as well as the Kata runtime, which is their own open source, I guess, quote-unquote proprietary runtime that they have. And you can swap out what hypervisors it's using to manage the virtual machines using a project called Virt Containers, which again is just a third-party software that allows you to abstract what hypervisors are being used at runtime. The other notable virtualized container runtime is runv. It also supports multiple hypervisors similar to Kata. And the interesting thing with runv is that Docker can use runv as its runtime implementation instead of runc. So by just changing a configuration, Docker can become a virtualized container runtime engine, which I think is very interesting. So that's all we have on container runtimes. In the next section, we are going to dive into container orchestration, what that means, and a variety of different orchestration softwares.